On this episode of the Dairyland Initiative podcast, we're going to be talking about how to cool cows with water. Hi, I'm Courtney Hallbach.
And I'm Nigel Cook.
And this is the Dairyland Initiative podcast,
where we get to discuss issues related to the housing and management of dairy cattle.
Let's dive in.
Well, today, Courtney, we're going to talk about how to cool cows with water.
It's a timely topic since it has been incredibly warm here in Wisconsin.
It's been like a Turkish tram driver's jockstrap out there.
Am I allowed to edit that out?
I don't think so. I think that's one of my better lines.
Oh my gosh, we just...
It's hot, people. It's been hot and humid.
Yes. So, as we're going through our list of what to talk about next, I thought it was worthwhile to at least do something on soaker settings for cows.
I think this is the end of our summer sequence of trying to talk about cooling.
Yeah,
it's been so hot.
Yes, but I'm sure this fall is going to continue to be hot. But we're going to move on by then, okay? I'm hopeful we're going to be talking about other things.
I think flooring and a few other things are coming up, so yeah. I'm excited about that.
Yeah, but first cooling cows with water. So get into it, Dr. Cook.
Let's do it. We've talked a lot about cooling cows without water.
Yeah.
So ventilation to get the heat and the moisture out of the barn, heat exchange.
To create that fast-moving air on the cows.
And, until death do us part, fast-moving air over the resting area. That's the key.
And that's because the research has said it works.
The research says it works, but as it gets hotter and in certain climates, I think we have to appreciate that using water is an important part of cooling as well.
Yeah.
And we've, I think with Dr. Jennifer Van Os, we've kind of talked about the thermodynamics and the science behind this. And now I've come along, we're going to talk about some of the practicalities of it.
Yeah. You're going to tell us how to set it up in the barn.
I'm going to try. We can use water in a number of different ways. We can soak the cow, which is kind of like mimicking sweat. Cows do sweat. They don't sweat particularly well, but we can improve that by sticking water on top of them and allowing that to evaporate. So that's one way. But we can also use water to cool the air before it reaches the cow. And we can do that either just with gentle misting, using very fine droplets of water, or with evaporative cooling pads.
And I'm guessing climate, where this barn is located, is going to tell us what method we should be using.
Yeah, for that last part, so soaking works whatever the climate. Evaporative cooling and misting really only works under lower humidity conditions. And
so
that's
not
just
Wisconsin?
It can work to a degree on some of the less humid days. You just think microclimates. It's not always as humid everywhere as you might expect. As the temperature increases, the air can hold more water, but there's a limit to how much it can hold, and so under very high humidity conditions, the air just simply can't take on any more water, and so water doesn't cool the air under those circumstances.
I thought you went to school for a veterinary degree, not an engineering degree.
Oh, what I've learned over the years, you wouldn't believe. We can also use water in one last way, which we'll touch on, and that's using the water below the cow to conduct the heat out of her, using cooling mattresses. So we'll touch on that at the end. That's my plan.
I think I'm going to stay awake for this podcast episode.
All right. Well, just as a reminder, it's all about temperature gradients. So the idea of using fast-moving air is to move that air, or that hot, humid air, away from the cow. So that's how we cool our coffee in the morning. So just as a reminder of that.
Like we're blowing across the surface.
Yeah. Yeah, but as it gets hotter and hotter, there are some challenges that the cow undergoes in maintaining her homeostasis, which Dr. Van Os talked about. And this is a very old experiment, and you can tell that because this was the average size of the dairy cow.
The average size was?
The weight is 500 kilos, which is just a little over 1,100 pounds.
Yep, we're bigger. Those are jerseys, maybe.
Well, they were little little black and white animals. These are probably data from the late 1950s, because we just simply haven't revisited a lot of this.
Yeah, why not? Come on, folks.
Something about getting rid of a lot of federal employees that used to do this research. So I don't know that anybody's going to pay us to do a lot of this anymore. This is attempting to show how animals, cattle here, lose heat through sensible losses, which remember is without a phase change. And we're highlighting as the ambient temperature increases from here about -1 centigrade to 27 centigrade, so about 30 to 81 Fahrenheit is the temperature range. You can see here that the sensible heat losses actually decrease compared to the total heat losses. And so you go from about 79% of the heat losses being sensible at freezing conditions to only 20% under conditions of heat stress.
And why does this matter?
Why this matters is because you need to focus on latent heat loss under those conditions, and that's the bit where we're focused on that phase change. So the evaporative cooling, the soaking comes into play. So the cow is ever reliant on that type of heat loss.
Okay, so you've convinced me that we need to do something.
Okay, so the something that most people do in the US, about 85% of barns, you'll see these things.
The
feedline
soakers.
soakers.
Yep, feedline soakers.
And I hate them.
What?
Absolutely hate them.
Where is this coming from?
With a passion. Because it just chucks so much water into the alleyways and it screws up all my handling systems. And we proved multiple times that these soaker systems didn't improve line times.
And that's what you care about.
And that's what I care about in the summer, however, they don't make much of an impact on line time. Airspeed in the resting area makes that impact.
There's a but.
But they do impact body temperature, feed intake, and milk production, which is obviously important.
Yes.
And why a lot of farmers choose to do this, even though they screw up my sand manure handling systems. So how do we go about soaking the cow? How much water? How frequently? And we've changed a bit over the years, and there's been some good research. This is one of my favorite researchers, Berman.
Yeah.
You'll see some slides from Berman in my
This is
my
a
slide
classic.
sets. And this is just looking at the time after skin wetting relative to the surface temperature on the y-axis here. And we were looking here at different airspeeds. So it also gets back to the importance of airspeed. So you don't get a lot of cooling with water unless you move the air over the cow.
Yeah, it's
So it
important to
does-
have the two.
That convection loss and evaporative loss. So you need that 200 to 400 feet per minute to get the temperature drop of the skin. So that works. So this is time after wetting. So when we're asking the question, how frequently should we soak? It's generally the effects are done by about 10 minutes. 10 to 15 minutes or so, something like that. There's really not a lot of residual impact of that wetting after a quarter of an hour. So it isn't that we have to soak the cow every 5 minutes. It isn't that we would soak them just, once a day or something like that. To get this sustained effect, you do have to soak them fairly frequently.
But I'm guessing how long you're soaking them for and at what temperature threshold you start. That also plays a
so
role.
when you think about practically how you implement this on a farm, you don't want to waste water. You want to use water efficiently. And using too little water is ineffective. So you can use too little, but obviously you can use too much. You get to a point of there isn't any sort of greater benefit of absolutely drowning the cow in water. So typical recommendation is around 1 gallon or 4 liters per spray application, which would reach typically 2 or 3 cows at a feed bunk. And using that interval about every 10 to 15 minutes would be the sort of range of interval of soaking that we would use. And obviously kind of adjust those recommendations based on climate. And I think what Dr. Van Os was able to show, and one of the sort of old wives' tales or something that we would hear, is everybody's obsessed with droplet size and avoiding very fine droplets because they'd insulate the cow. And it doesn't matter.
Okay.
She's looked at it. It doesn't matter.
Yep.
We generally use these low pressure systems which have fairly large droplets anyway, which, if anything, that's the better way to go. But you need a control unit, and this was Edstrom is a very common one we see. There's several
Plenty
other
out on the market.
manufacturers, and this particular unit has 2 temperature activation settings, so it can run 4 zones at each temperature level. So what's typically we start soaking around 70 degrees Fahrenheit.
Okay, so 21
degrees centigrade. And we used to soak the cows for like 2 minutes.
Oof.
And
That's a lot of wasted water.
That's a lot of wasted water, and we don't need to do that with these low pressure systems. So about 0.3 to 0.5 minutes of actual soaking time, and that's called the shower time in these units. So that's what we'll commonly see. And you can set the interval time. Now you have to remember the interval in the unit is the interval plus the soaking time of the other 3 pens before
that's really key there.
Cycles back to the pen. So you have to remember that. So it's 12 to 15 minutes, but you have to factor in half a minute, and the 3 areas.
Got it.
So that would be typical at around 70 Fahrenheit. And because you can, and because there's probably some benefits of soaking a little bit more frequently at higher temperatures, usually around 82, 85 degrees Fahrenheit, so 28, 29 centigrade, we'll see these units programmed to soak more frequently.
Okay.
So still for 0.3 to 0.5 minutes per cycle, but then you can drop the interval down to 6 to 10 minutes would be common.
Okay.
So I think we've kind of learned that these systems help on the dry matter, milk production,
body
temperature side. Don't help so much with the lying time.
So you're saying prioritize fast-moving air and then supplement with water.
Yeah. That would be the way to go, because we want to try to avoid this.
You want to just
dumping
water into the alleyway?
In the alleyway when there's no cows there, and there's nothing about that system that knows that the cow is milking. Yeah. So the cows can be out of the pen, and I'd walk on a farm and it's just
running.
Just hate this. Just spraying
Is this
water.
what keeps you up at night, Dr. Cook?
It's another one of those things that keeps me up at night. Now, you can solve that with a fancy nozzle.
Well, there's new technology emerging.
Intelligent soaking. So you can use ultrasonic sensors, infrared, whatever they are. And there are a number of models available now that we're starting to see this, that actually sense below the nozzle whether there's an obstruction, usually a cow.
And it will set off like about 10, 20 feet, right?
Yeah.
Or something. Not just an individual headlock, but a row of headlocks.
A row. Trouble is, I think they're a bit pricey at the moment. And
just let the market get saturated.
At least in the US, water's still relatively cheap. So
and available.
That cost differential.
Depending on where you are.
Depends where you are, yeah. That cost differential is kind of tough to think about. But if you're in a situation where water's expensive, this technology's undoubtedly going to get cheaper.
Or you just want to use water efficiently.
Yeah, or you're very mindful of that. So this helps. This absolutely helps. So it only turns the nozzle on when there's a cow there. And then there are places that you can soak on the farm less frequently, but you can ensure that the cow's there.
Yeah, strategic use.
Exactly.
Soaking.
So holding areas are the prime example of that. And I often say with my UK dairies that sort of call, where should we, what should we do for heat stress? We're getting these hotter summers. This is a good place to start.
The holding area,
You can make an incremental improvement here because you're putting water on cows. It's relatively cheap to do. You're making sure that the water gets on the cow.
So place some fans up to
and put
get
fans
the dual
over,
fan,
help
fast moving air and water.
Yeah, exactly. So these are big IWOB nozzles. They have a big weight on the end, so you can see them sort of hanging down from the ceiling over the holding area, and they cover about a 30-foot spread diameter. So most of our holding areas are within that. So just a single nozzle just hanging over the middle of the holding area, and you put a row down, you can cover quite a lot of area with these things.
Yeah.
And it makes sense to me. It's efficient use of water. Cows are there. They're going to get cooled. Now, it cools them for about 15 minutes.
Yeah.
So it's not going to last a long time, but it can help.
Mm-hmm.
Some people have used motion sensors and put soakers on exit lanes.
Yeah.
So as well as soaking while the cow's waiting in the holding area, they can go through a shower station. And I was kind of intrigued by this because you could build little voluntary shower stations in a
within a
freestyle
pen. Yeah.
Yeah. and the cow could, enter that area, get a soak if she wanted to, when she wanted to, and then exit. And kind of intrigued by that. I don't think I've seen
That hasn't caught on.
No, that idea hasn't been embraced, but we've started to see some strategic soaking around robots, for example, where you can use this again sensing technology. Gate opens, little nozzle goes and activates. You put the water on the cow as she exits, and in a robot, 3, 4, or 5 times a day she can get a soak, and that can help. Rarely, but we do have a couple of examples where you can just put soakers up over the cows in the parlour itself. So that's another targeted strategic use of water.
Are you concerned with water getting onto the udder at all?
I was, but I think Dr. Van Os has kind of shown that wasn't such a big deal. Yeah. And again, it relates to the amount of water, droplet size, how much dripping you're actually getting, but most of the dripping is off the sort of flank of the cow, not necessarily dripping all the way down to the teat. So moving on from soaking, we can use water to cool the air before it reaches the cow.
And that can be done with misting systems.
Yeah, so this is, you'll see a little frame in front of the fan in this kind of setup, and it will have a very fine mist. So this is where droplet size does matter. So this is very fine, and it's cooling the air.
Yeah, it's not getting on the cows at all.
That's the goal anyway. And you'll see, again, different manufacturers will have slightly different setups for this. But this is what we call high pressure fogging to help cool the cows. Uses less water. Really does cool the air.
Is it better, though, in low humid environments?
It needs lower humidity environments because, again, the air can only take up so much water. As the humidity increases, these systems become less effective. Yeah. But, we have these systems in a number of Wisconsin dairy farms, and there's a lot of days where these can actually be very, very effective. And if the amount of water available on the farm is a challenge, then this can certainly add to cooling. But if you're in a low humidity environment, Australia, Arizona, the corral cools that we see in dry lot dairies will use this type of approach. So a good use of water, in my opinion, to help cool the air. And it can be kind of low tech. This is just a fine hose with tiny little holes along the inlet of a cross-ventilated barn, and you can see the air just picking up that mist and help cooling the air as it enters the barn. So it doesn't have to be particularly high-tech.
Except there are a little bit more high-tech solutions such as evaporative cooling pads, right?
That is the next step, and that really lends itself to these long inlets that you see in cross-ventilated barns. So not so much tunnels where the inlet is smaller relative to the size of the barn, but with that sort of long axis inlet, you can put an evaporative cooling pad along that entire inlet.
And if you do that, there are some design changes than what we would see in a normal cross vent with
so that is a sort of honeycomb pad that we're dribbling water through, and the air goes through that pad. Well, there's a resistance there, so it's going to impact inlet speed, and there's kind of a time that's needed for that water to cool the air. So you generally don't run the inlet speeds as high with this type of system as you would a normal 500 to 800 feet per minute.
It's so closer to 400.
Exactly. So the technology behind this, or the physics behind this, is a bit complicated. And,
I'm going to tune out for this part.
So I've got this lovely psychrometric chart here, Courtney.
Yeah, makes me want to puke.
And I'm hands out. Let's give a shout out to Mario Mandaka, who actually showed me how to use this.
Yes, please teach me.
I know just enough to be dangerous on this
thing. Scary.
So at the bottom, you've got the dry bulb temperature. Do you know what the dry bulb temperature is, Courtney?
No, I don't. Do you?
I'm going to explain it to you. It's the air temperature unaffected by moisture or radiation. Got it?
Definition.
This line here takes us from the dry bulb temperature. It's the green line, if you're watching this. That takes you to the wet bulb temperature.
Oh, that's
Do you know what the wet bulb temperature is?
I think you're going to read a definition.
I'm just going to read it off the slide here. It's the air temperature cooled by adding water. So it's that function of adding water, cooling the air. And it goes to, at a point of 100% relative humidity, it equals the dry bulb temperature.
Okay.
Okay. So at lower relative humidity, the wet bulb temp is less than the dry bulb temp.
Okay.
Okay. So because you can add water to it, temperature goes down. That's my plan anyway.
Okay.
These lines, these curvy lines, relative to the water carrying capacity of the air, that's the relative humidity. Okay. So as the temperatures are going up, water carrying capacity of the air goes up, the relative humidity curves around. So these different lines are at different levels of relative humidity.
Okay.
Got it?
Sure.
And the relative humidity is the percentage water vapor in the air compared to the maximum carrying capacity of the air. That's the percentage.
Why are we going through this?
Because I'm going to show you how cooling pads work, which is kind of very exciting. Because here you can kind of see the direction of these arrows is really telling you what type of cooling you're undergoing. So the sensible cooling and heating is a sort of parallel line. But now we're going to go with this diagonal line here, because up there is evaporative cooling. And that's what we're talking about here.
Yep.
All right. So let's just find a point on this wonderful chart. And that is the dry bulb temp of 80 degrees, right? At 60% relative humidity. It's right there, Courtney.
Okay.
See it?
I see it. It's nice and red. I like it.
Okay. We are now going to use a cooling pad, and we're going to increase the humidity.
Wow.
Because we're going to add water, yeah?
Uh-huh.
Okay. So we're going to increase the relative humidity to 85%. And then ask the question, how cool will the air be?
And this graph can tell us?
It can, because now we're going to drop the line down there and read it off. What does it say, Courtney?
I can't read.
Okay. So we've gone from 80. It's down to about 72.
Okay, folks, if you are watching, you will see how fine print this whole slide is.
It is quite fine print, but this is the psychrometric chart. You can Google it. It's a thing to behold.
Well, thanks for that little tutorial, Dr. Cook.
That little physics lesson. So I was enamored by this when Dr. Mundaka showed me how to use it. I thought, okay, this is cool. Bottom line, as you add water to the air, you can cool it. So we're going to go back to our friend Berman in the sweltering hot conditions of Israel, where a lot of his studies were done. And we're now at 93 degrees Fahrenheit,
Whew.
34 centigrade, and we're exploring what happens to air temperature as you change relative humidity with evaporative cooling. So the cooled air is now going to be at 65% relative humidity. And if the ambient conditions are low humidity, so only 15%, we could drop the air temperature by 24 degrees Fahrenheit or 13 degrees centigrade.
That sounds fantastic.
Pretty darn good. Well, that's pretty dry, so that's kind of Arizona-y. So now at 35% relative humidity, ambient conditions, we're adding water to the air through evaporative cooling. We could get a drop of 12 degrees Fahrenheit or about 7 centigrade.
Okay. Pretty good bang for your buck.
So now it gets more humid. Now we're at 55% relative humidity.
Wisconsin.
Yep, we're getting there. Now we're fairly ineffective.
Yeah.
Evaporative cooling
worth it.
isn't doing much.
What, at only about a
Minus
degree?
1.
Yeah.
But about a degree. So just really demonstrating the investment in this type of technology that's going to be much more useful in those lower humidity environments.
Yeah.
In Wisconsin, we've got barns that have pads. We've actually got one on our campus. Yep. And, it's not super humid all the time. So we'll get a drop of, 5, 10 degrees Fahrenheit. And you can feel that. But you can also feel the humidity.
Yes.
A lot of those barns will run probably max out around 80, 82, when other naturally ventilated barns are in the 90s and cows are sweltering. But it's humid. There's moisture in the air that gets problematic with bedding management and things like that. And actually, when you calculate the THI, it isn't that much different.
Yeah, because the high humidity.
Because of the increase in humidity. So where are these benefits for these cooling pad barns? Well, they're usually climate control barns. No flies, no bunching. There's a lot of other benefits that I think they see. And there's this little problem of cooling pads.
Of maintaining
Maintaining
them.
them is an absolute nightmare.
Yeah.
These are our cooling pads that we saw on campus after some building work. And dust and debris.
That seems to be happening all the time on this campus.
It's pretty much a constant, so cleaning these things is pretty much a constant too. And we've shown power washing, can actually improve airflow through these things.
Wasn't it like a couple 100 feet per minute?
Yeah, 15, 20% improvement. Yeah. So it does make a difference. And, it's work. It's another task that a farm has to do. So we've actually seen a lot of mechanically ventilated barns now built without the cooling pads. And for the most part, even without water, they get through most summers. And I think this summer is maybe challenging them. Yeah, this one has been a real stinker. So there are clear benefits to using water in this type of situation, but there are disadvantages of maintenance, of blocking the inlet, of slowing the air. As the air comes in, if we're only hitting about 420 feet per minute, we probably need a baffle or something to assist the air fairly early on in that barn to pick the air.
Fast-moving air in the
pick
resting
the air
space.
up and speed it up through the cow space. So our last use of water was the conductive cooling.
Yeah, this came about with some engineers and Mario.
On campus, we tried this I lost 2 summers of my life on this one.
I think I was just starting, and that's maybe also when you lost a few hairs on your head.
Yeah, a lot of grey hair, I think. So there's some engineering behind this. Well,
what was the idea, I guess?
Basically to develop a mattress that we pump water into to help cool the cow through conduction.
While she's lying down.
Which would also work in high humidity conditions.
Okay.
Yep. So that's the concept, and you can kind of see the foam that we chiseled out and made these little spaces for all the water to channel underneath the cow. And we installed this at Arlington and tested it for a couple of summers. Version 1 had a pump that pumped water into the mattress and a pump that pumped it out.
And don't I remember one of those pumps failing and you guys flooding the pen?
Yeah, so the pump that was working to pump out the water failed, and so we had a situation where it just carried on pumping water into this giant balloon, and then it kind of exploded and made a lot of mess. And yeah, they didn't like us much after that one.
No, I'm surprised they let you back out to do research.
Yeah, we have a patent on this thing, which is interesting, but we tried, and it does theoretically work, and some of the other researchers at Cornell and other areas have shown this, that you can achieve about 1 degree Fahrenheit drop in body temperature through this type of situation. And this little infrared graph here shows where the high temperature spots are, and this was comparing with sand bedding, which is an insulator. So we can drop the temperature, and we were just using well water, so not cooled water. It's just coming out of the ground at 55 Fahrenheit, 13 degrees centigrade, pumped in through this mattress. Again, dropping temperatures about 1 degree Fahrenheit, 0.4 degrees centigrade compared to sand.
Okay.
That was the good news. The bad news was it was rather difficult to get the cows to lie on them in the first place.
Yeah. Remember, you've shown that cows prefer sand.
They do, and we kind of confirmed that in this study. So we've got 8 stalls with our cooling mattresses on the right, 8 sand stalls, and you can see throughout the day kind of where the cows prefer. So even if they're cooler, we've got air movement, we've got other things going on. We're not soaking at the feed line in this study, but the cows clearly still preferred
sand
to lie in the sand stalls. So there is a challenge of really getting the cows to utilize that.
Yeah.
Yeah.
So that's why it hasn't taken off.
There are commercial products out there that use this, but in our hands, it was a fail.
Okay.
So the physics worked, the aesthetics and the cow choice didn't. Cows choose sand. So that's where we were at, Courtney, with using water on farm. Yeah. We talked about using it to soak the cow, but then also to cool the air before it reaches the cow. And then just touched on the possibility of conductive cooling, which is a hope, but currently is a challenge.
Well, I think this was a comprehensive overview of using water on farm to cool cows. I'm still going to
have nightmares about the psychrometric chart.
That, but also I'm still going to put fans up over my stalls and in the holding area. And
that's a good place to start.
That's number one. And then number two, I'll consider using water. So hopefully people have taken away some good information about how to implement water on farm to cool cows so that during these periods of extreme heat stress, there are some solutions.
Thanks for joining us.
Thank you. The Dairyland Initiative is supported by industry leaders who are advancing cow comfort worldwide. We would like to say a special thank you to our premier sponsor, Saputo, who is providing the global community with high-quality dairy products made from high-quality milk from healthy and well-cared-for animals. We'd also like to say thank you to our other sponsors, SaveCows.com, Zinpro, GPS Dairy Consulting, 40 Barn, SureGain Trout Nutrition, Munters, J&D Manufacturing, VES Artex, Ventec, and Kestrel Instruments. Thanks for tuning in to the Dairyland Initiative podcast. Want more Dairyland Initiative? Be sure to subscribe to our podcast, follow us on our socials, and visit our website for all of the latest recommendations in dairy cattle housing and management. See you next time.